Can you hear me? Great. My pleasure to be here. I want to thank the organizers for the invitation and to the awards committee for the award. One of the conundrums about industrial research is that if something is really successful, you get to talk about it a lot internally, but not much externally for a while. So we've been waiting about 15 years to tell you about some of the results that we're going to hear, because many of these results have been very successful commercially. So, as John said, today I want to tell you about the interplay of acid activity, shape selectivity, and mass transfer effects in the production of some of the very important aromatics. We really have brought together all of these different effects to create catalysts which have properties unlike many of them that have been demonstrated for these kind of technologies. So we're really going to talk about molecular design, function, and also commercial application, and I'll show you how these catalysts have been forming commercially. But first I want to build on this interplay of the three items I mentioned. So aromatics is a big business. The manufacture of high-value aromatics can be demonstrated as seen in this slide. You start with the olefins that you get from cracker separations, whether the FCC or steam crackers, and then you combine them with the base aromatics. So in the case of ethylene, I can combine with benzene to make ethylbenzene, and propylene combined with benzene to make cumene, two very important chemicals. And then from the reformer, I get toluene and xylenes, and I can make paraxylene, which is a very important molecule that I'll talk more about. Can either get that by disproportionation of toluene, or from xylene isomerization, or from the transalkylation of heavier aromatics, as shown below. Now these aromatics, as I mentioned, are extremely important industrially. Ethylbenzene is produced at about 60 billion pounds per year, and it's used to make styrene and polystyrene. So you get dehydrogenation to make styrene and polymerization. Cumene is oxidized to make phenol, which can be converted to bisphenol A, and then on to make polymers like polycarbonates. And the one we'll speak mostly about today is paraxylene, which can be oxidized to terephthalic acid and combined with ethylene glycol to make polyester. So together you can look at the volumes there. These are some of the world's most important chemicals, so selective routes to these chemicals is critical. So paraxylene can be made in a number of ways, and it can be produced via equilibrium and through selective processes. So if we look where the pointer is, these are some of the equilibrium processes. We have xylene isomerization, where we basically take xylenes to equilibrium. And as nature would have it, the isomer that you want is paraxylene, and that's only produced in 24% in equilibrium. So we can produce it that way. We can disproportionate toluene, then I get a mole of mixed xylenes and a mole of benzene, and the paraxylene is also produced in 24% isomer selectivity. And then I can also get it by transalkylation of toluene and, say, trimethylbenzene. And again, I produce equilibrium xylenes. So lots of ways to produce an equilibrium nitroxylene. Now it's been known for some time that there are some selective processes to make paraxylene. I can disproportionate toluene as I did previously, but I can selectively make paraxylene. So the selectivity there is greater than 24% to the isomer. And that's done in a zeolite, one of our favorite zeolites here, ZSM5. And I'm going to talk much more about the role that ZSM5 plays in achieving this. Now, it's fortunate that I can do selective catalysis to make paraxylene, because the separating paraxylene from its isomers is not trivial. You can look at the boiling points along this top row and see that they're very close. So distillation is an ineffective method of isolating the isomer that I want. But luckily, the freezing points vary, and paraxylene has a much higher freezing point than the other isomers. And this really lends itself to being able to do a crystallization process. So there are two commercial routes for recovering paraxylene. One is by crystallization, it's a two-stage process, and then one is by adsorptive separation. and it's a UOP-Parex type process. But still, in catalysis, the separations end of the plant is often a very expensive part of the plant. So I want to make the molecule that I want, and I want to make it without its other isomers. So the question is how can we do that in sufficient selectivity to minimize or eventually eliminate the separations part? So we have a proverb that's developed over the years in ExxonMobil, and the proverb is, it's much easier to teach an old zeolite new tricks than to discover a new one. And in the case of certain zeolites like ZSM-5, we've taught ZSM-5 a lot of tricks over the years. It's probably the world's most versatile of the zeolites. Some of the other zeolites like MCM22, which we use for ethylbenzene cumene synthesis, has also been very productive in its versatility in different reactions. So ZSM-5 has two types of channel systems. It's got a sinusoidal channel, which winds through the crystal, and a straight channel. And you can